Alright, we're supposed to come up with a strategy in the free body diagram to find these member forces CE, it's down here, and DE, right there, and then DF. And boy, that just calls out right away. Just do a method of sections as your free body diagram. Let's try to get them all into one if we can, and then see what happens here. If we do this, then we don't really have to show all the members that we haven't cut. I like to do so because it helps me keep my frame of reference of what's really going on, what I've included and what I haven't included. Some people like to just put a little hash mark in there to try to indicate the sort of solid pieces that they're not including. Again, I don't like doing that because I like to see the whole structure. All right, so we got 6 kips applied here at point C. Over at A, we just have that vertical reaction, normal to that horizontal surface. So there's AY, and there's B, nothing happening at B. At D, there's joint D, and then probably that top chord is going to be in compression, that's FDF. The bottom chord is probably in tension, that's FCE. And then we got FDE, and let's just kind of look at this and see what might happen. Right, that from the magnitude of the reaction that we're going to get here, what would that be? Well, both, let's see, this 6,000 pound force is wow, it's at the 1 to 5 kind of ratio here, right? This whole span is got 1, 2, 3, 4, 5 equal spaces, or one space over, so that means 80% of this load is going to go over to AY, so that's 4.8. And then this other one is got 2 spaces compared to 5, so that means 40% of that, or rather 60% of that load, the closest one is going to take that fraction up, and that would be 3.6, and that's going to be, let's do the math in our heads, eh? There's a 7, there's a 8.4 kips, right? Now, you could have just argued simply, hey, look, whatever the reaction at AY is, it's going to be larger than just 6,000, and 6,000 or 6 kips is the only thing that shows up here. That means that if AY is bigger than that 6, then that means DE has to be going downwards by summation of forces in the Y. Right? So find FDE with summation of forces in the Y. Right? That will equal AY going up minus 6 minus FDE in its Y component equal to 0. We do have to know AY to be able to actually solve for it, but we could do that from the global equilibrium. Right? Now, that would be one of them. The other one then would be, well, how do we find then CE? Well, let's sum moments about point D. Right? So find FCE with summation of moments about point D, and we can take counterclockwise positive, and now we're going to have to find all the dimensions here. We got an isosceles triangle, so that would be our AY is negative AY times our moment arm. That's going to be 3/2 of 12.5 feet, and then you'd have the 6 going the other way, so plus 6 times 1/2 of the 12.5 feet, right? That would be its moment arm right here, 1/2 of that 12.5 feet, and then plus FCE times then its perpendicular distance, which is the 15 feet, and that would be set equal to 0. And that's, again, we have to know AY, but if we know AY, then we got one equation, one unknown. And then likewise for DF, we come down and we choose then summation of moment about point E. Right? The place that we sum moments does not have to be included on the free body diagram. And there again, you can see we've got this minus AY. Now we'll have 2 panels, so 2 times 12.5 feet to get a total of 25 feet for that moment arm. And then you've got the 6 going in the other direction, 6 kips times your 12.5 foot moment arm, and then you'll have FDF times 15 feet, and that will be set equal to 0. So in each and every instance here, we do need to have AY in order to find it, but that's the direct, simple way to go about, especially with parallel chord trusses, this technique. The diagonal, when there's only one that has a vertical component, usually some forces in the Y is going to get you that one, and then sum of moments associated with one of the chord joints to get then the opposite chord force.